All right, so today's lecture is on deep learning. Maybe a little lower energy than most lectures, a little tired for obvious reasons. I actually did want to mention a little bit about the election that happened last night. Not to be political at all, because I don't think that's that's not the right place for it. But I think undeniably, actually, one outcome of the election was that it was a complete failure of practical statistics in terms of the polls, right? So apparently, not only the polls that we knew about, and so that's the ones you're going to be analyzing, maybe in hindsight now in your homework, but also the ones that were apparently in both campaigns internally they were all sort of aligned that, it looked like a pretty clear win, and they were all completely wrong. And so I think it speaks to some of the fact that there are underlying assumptions that we make, even though these things are all data driven and they're mathematical and we have these p-values that tell us things supposedly, they're all based upon assumptions, like assuming a certain distributions over voter turnout and things like this. And when those things don't happen, you can have wildly divergent results from what all these sort of very complex models were telling you. And so I think it's actually quite interesting from a purely mathematical standpoint, or maybe maybe more sort of from an empirical standpoint, just to see how much all these statistics were wrong in some sense. And so I think there's actually been a lot of recent events that happened like this. So someone did their tutorial on the Colombia referendum, which was similar. They voted against peace with the FARC. Brexit, of course, which all the polling says was gonna not pass narrowly, and now this. So just from a statistical standpoint, it is interesting to see how the assumptions that we're making about these models are really breaking down in a lot of cases, and that does speak to some interesting elements going on. So, for example, if anyone, I know you're supposed to already have your projects and people are changing them as you go. So if you do want to do like an analysis of the election, this one or any other one, that would probably be a good final topic. Maybe seeing what the polls before said versus what actually happened. That would make for a very interesting analysis. So anyway, that's all I'll say about this. I have many more thoughts, but I will not speak to any of those. And we'll jump into deep learning, which is actually one of my favorite lectures to teach, both in this class and in other ones where I teach it from a slightly different perspective. But that's all. I'll preface the class with that. Yeah.
I wanted to ask about the polls. I don't know whether we can ask about it or.
Maybe we can take like 2 minutes and do that. Sure. What was your question about the polls?
So you said that the polls complete failure in predicting the outcome. I seem to, like, from what I've read, it seems like there's a large majority of Trump supporters who weren't participating perhaps in the elections for the past two elections,
right,
who weren't participating in the polls, and just for the election they went out of their homes, drove to their election place and casted their vote.
Right.
Is that something that the polls did not capture?
Yeah. So I'm not a political scientist, so I don't want to speak too much to the polling here. The fundamental problem, as from the mathematical standpoint that I understand it, we can kind of talk here, is about this issue. So it is the fact that essentially polls have to make assumptions about likely voter distributions because not everyone in this country votes, and you have to basically assume that the future will be like the past in some extent. I mean, you try to measure enthusiasm and things like this, but ultimately you're basing your forecasts based upon what you've seen in the past whenever you whenever you decide what your sample is going to be, essentially. And you're absolutely right that the sample that we saw last night was not representative of the sample that people were using in all camps, right, to base their models upon, and so that was the main cause for divergence, it seems like. Okay, so that's all I actually want to say about that. But it's actually a very interesting thing from a purely kind of from the interaction between science and the data science and statistics and actual policy. It's a really interesting topic. So. It would make a great bit of analysis, I think. All right, so let's talk about deep learning. First of all, tutorial evaluations are due tonight. I never actually specified a late day policy. I meant to, but I forgot, and I realize it's pretty late now. So you can go ahead and use late days on that if you want to. I'd recommend you don't. The normal, I think we'll have a normal 3 late days if you really want them. I'd recommend strongly against it. They shouldn't take you that long to do. I personally would think it'd be kind of a waste of your late days, but you're welcome to do it if you need to. Secondly, I'm traveling, as I mentioned, next Monday. It's not on the schedule yet. I will shift lectures as needed to account for that. We're going to have a guest lecture. I believe it will be on a topic related to interactive data visualization, but I will send out details when I can confirm that. And then finally, I did send out an updated policy on the project midterm reports. So those are going to be due anytime between this Friday to the Monday after the following Monday. So a week and a couple days. And I will respond to those on a rolling basis. So when you write, I will try, not be every day, but within a couple weekdays at least, I will respond back and give you feedback on that. You only get one set of feedback, so you cannot submit multiple times for multiple feedback. You can get one set, but the advantage of doing it early is you have more time to respond to the feedback, you have more time to incorporate the feedback, first of all. And secondly, there's a good chance I'll respond faster at the beginning. And so by the end, if you wait till the last day, that's getting, I'll try to respond that week, but that's Thanksgiving, and you're getting kind of close to the end there. So I would highly encourage anyone that can to submit early. All right, so let's get started. Let me get some chalk out. All right. This lecture is on deep learning. And deep learning is one of the more kind of both trendy and fascinating topics, but also one of the ones that is a little harder to situate in data science, because it isn't really about data science in any way, right? It's about these very advanced, very sort of complex machine learning models that are often seen as kind of black boxes where you almost can't infer anything about what's going on underneath the hood from them. So I want to spend some time talking a little bit about sort of the recent history in machine learning and when these things came about and why they're so popular. And then I'll talk about machine learning with neural networks. So I'll talk about the 3 elements that we always describe here. How do neural networks fit into that whole framework? Loss function, hypothesis function, and optimization. I'll talk then briefly about training neural networks. I will not go into detail about the algorithm here, which is called backpropagation. I love teaching backpropagation, so I'm sort of sad that I can't teach it. But I think for one lecture, we're going to have a hard time getting through all this anyway. And so I don't want to push things too much. And the good news, of course, is that you don't actually need to implement it anymore. You can typically use existing libraries for that. I'll talk then about some specialized neural network architectures like convolutional networks and recurrent neural networks. These are actually really the things that have made deep learning kind of prevalent over the last few years. And then finally, I'll conclude with a little bit of discussion about how you may want to go about using deep learning in data science. And it's not maybe the ways you would sort of think, which is just apply these things off the shelf. It's a little bit more complex than that, but I'll talk about how I see currently, at least, the best interface going there. All right, so let me talk a little bit first about some recent history in machine learning. So this is a chart I made a few years ago. It's actually probably, I don't have 2016 yet. I should probably get that in when I have a chance to. But what this shows, this is sort of an arbitrary plot, but what I'm showing here is I'm looking at papers according to Google Scholar. So I scraped papers from Google Scholar. And I looked at the number of papers that had the word neural network in the abstract or title, and the number of papers that had machine learning in the abstract or title. And I divided the first one by the second one. So here, it can be any number, but it's a ratio. But numbers, higher numbers mean there's more neural networks than machine learning, and lower numbers mean there's more machine learning than neural networks. And this actually tracks pretty well the history of neural networks in machine learning. So they started getting popular in the late 80s when people not invented, because it's actually been around in many forms in many different ways before, but they popularized the backpropagation algorithm for training these deep, or training, not deep, but just neural networks. And this kind of popularity peaked in the early to mid 90s, where people started applying these to life domains. They started getting some interesting results. But then around 95 or so, support vector machines and boosting really kind of took over from these domains. And it's not actually a mystery why they did that. At the time, on the computing hardware we had support vector machines and boosting actually just performs better on a lot of problems. On the scale of data we could actually sort of process and the problems we had, they just kind of worked better. And a lot of people I think attribute that to some sort of malice or conspiracy to keep these things down. I don't think that's the case. I think it just seemed pretty rational. They didn't work as well. They seemed harder to train because they weren't convex. You had the problems of local optima. They didn't seem to, you seemed to get stuck in plateaus in a lot of spaces in the parameter space. And so that they sort of fell down in popularity for a while, to the point where I sort of joined the academic world between 2003 and 2005 or so. I started my PhD in 2005. And at that time, they were sort of at a low point, right? So no one wanted to do neural network research. It was kind of, the domain of sort of low-quality journals that have a lot of neural network publications in them, but no one serious did neural network research, except a few people who were then the founders of the people that are bringing back the movement. And then in 2006, some interesting things happened. 2006, at this conference called NIPS, which is a machine learning conference, there were a few papers on what was called unsupervised pre-training for deep networks. So we'll talk about it in a second, but deep networks and deep learning, as it's currently used, refer largely to just multi-layer, many-layer neural networks. And in 2006, what people realized was that if you pre-train these networks in certain ways. You basically pre-train them to recreate their input data. So rather than training them in a fully supervised way, you actually train them first in an unsupervised way, and then apply a supervised post-training. They worked a little bit better. And this sort of, people started thinking, well, maybe for the first time we actually can apply these deep networks to real problems, and we can really do quite well. I should add that since this has happened, pre-training has largely faded as a thing. People now just use straight backpropagation again, so we're back to how they used to be trained way back in the day. But of course, we have much bigger computers, much more data than we had back then, so these things are much more successful. And the real sort of shift point here, I mean, there were a bunch, but one of the big shift points was the publication of what's called the AlexNet paper. And I'll show some results on that in a second. But this was a computer vision application that did substantially better than, it was deep, what's called a convolutional neural network, which is substantially better than the next best approach. And it really kind of exploded these things, made them very, very popular. The next year, Facebook bought, or they launched their AI research center. Google bought DeepMind. A lot of sort of corporate interest kind of swarmed around these areas, and the interest has not yet tailed off. I mean, we are still on the rise of this. I mean, maybe it's, I should show 2016, but I'm pretty sure it would just be going up still. So we are actually, and you in the past 5 years have really experienced a complete paradigm shift in the nature of machine learning research. You may not even have known about it, but it has been going on kind of behind the scenes. So let's talk about a few examples here. So the AlexNet paper, which is one of the ones that kind of spawned this stuff, was essentially a convolutional neural network that on this one classification problem called ImageNet, it got 15.3% top 5 error rate. What that means is there's 1,000 different classes. You can classify every image into 1,000 different categories. You give your top 5 categories, and if any of those is right, then you get credit. If none of those is right, then you get no credit. But what's impressive here is the next best system, which used a really complex combination of engineered features, things based upon SIFT and all the other kind of, well, haven't mentioned that before. These very complex computer vision features, it got 26.1% error. So a huge gap there. You don't often see gaps like that in machine learning. Progress is typically, or in computer vision, right? Progress is typically slow. You have slow increments. This was a huge leap forward. And since then, it's now at about 3% the error. So it has, in the past few years, then it is improved in similar leaps and bounds with more and more complex architectures here. And this is a picture here, actually, of the architecture. And after we go through this lecture, you should be able to understand most of what that actually means. But here are some examples of the classifications it provides. So you take an image like that one in the top there, and it says it's a container ship with very high probability. Now, again, the universe of all images here are 1,000. So these seem really impressive because it seems like how on earth would you know those words? There's only 1,000 total words, but that's still a lot. To know that's a container ship over, say, a lifeboat is not that easy to do, and it actually takes quite a bit of seeming intelligence, right, to do something like that. And really, when I started working in machine learning, results like this would have been unthinkable. They were sort of, this was well beyond the state of the art, if anything that computer vision could do, and now it's kind of commonplace. And in fact, these are results from several years ago now, so we're doing a lot better than this. The one it gets wrong is this one, which is cherry, and it classifies it as Dalmatian. I think that's pretty reasonable, actually, right there. Doesn't see the cherries in the foreground, but I think that it's certainly incredibly impressive what it's able to do with this sort of mostly black box architecture. There isn't a lot of hand engineering going on here. A little bit more recently, and there are tons of examples in the meantime of really impressive things that have happened in the field of deep learning. One of the ones you may have heard about recently was the success of AlphaGo. So this company that, well, part of Google now, but called Google DeepMind, they developed a Go playing program. So Go is a board game, and it actually was one of the last what are called perfect information board games. That's games where you can see the entire board. You don't, it's not like poker where the opponent has hidden cards. You see the entire board. You see all your opponents' their current strategy, their current moves. It was the last one that computers really hadn't solved. So, computers could beat humans at chess for a long time now, but Go kind of held out as this last ground where humans still, because there are so many possible moves, humans are still really better than, or were still really better than computers at it. And so what Google DeepMind did was they developed essentially something used actually very similar techniques. They used convolutional networks, which again we'll talk about in a second, to develop, and plus reinforcement learning to develop actually plus a lot of things. They used Monte Carlo search and lots of actually quite involved algorithms here to develop a Go player which actually beat one of the former world champions in Go 4-1. So this is really kind of a breakthrough in AI as it's currently being perceived. I think actually in South Korea, this was viewed by as high a percentage of people as the Super Bowl is in the U.S. This is big news there. Even if in the U.S. we don't really care about Go that much, this is a big deal. What was that? Yes. Okay, so with that as context, I want to describe how this all works. Not quite to the level where you're going to really know how to implement it, but I want to describe what's going on here and what are these amazing models called deep learning models. A question? Yeah.
There's two things that I want to say. First is I think the same team is now taking on StarCraft 2. Mm-hmm. That's what I read. And the second is there was a recent CMU paper on how to fool deep networks, the facial recognition features of deep networks with glasses.
Mm-hmm. Yeah, so there's a lot of follow-on work to a lot of this stuff. I won't go into detail a lot of it. There's new deep learning news every week, it seems. Okay, so I want to talk about a little bit how this all works. What's behind these things, and really. Neural networks and deep learning I should say really refers to neural networks largely. There's some debate whether that means a slightly larger thing, but it for the most part means neural networks, which of a certain kind let's talk about. But the term neural network, and deep learning in particular, really is a subset of machine learning, and it refers to a certain class of machine learning algorithms. In particular, it refers to a class largely by the hypothesis function they use for that class. So remember, we have these three ingredients. We have hypothesis classes, loss functions, optimization. Neural networks use a very specific form of hypothesis class. In particular, they use, we'll see it in a second in much more detail, but they use essentially a composition of multiple linear operators, like matrix multiplications, followed by element-wise nonlinear operators. So things like the sigmoid function, or more common now, what's called a rectified linear unit. But importantly, it's just a combination or a composition of multiple functions, multiple linear operators and nonlinear operators composed together. That creates the hypothesis class, or that creates the hypothesis function, and I'll talk about much more what I mean by that in a second. After that, though, that really is what a neural network is. The loss functions you use themselves are usually pretty standard. If you want to use a classification, for example, you may use logistic loss, something called a softmax or cross entropy loss if you want to have multi-class classification, and then things like or hinge loss, and then things like squared error or absolute error if you're doing a regression task. So the loss functions themselves are pretty standard, and the optimization is actually pretty standard too. It's basically gradient descent. You optimize by gradient descent. It actually is a little bit of a variant on this, which we'll talk about, called stochastic gradient descent, but it is basically is just take gradients and adjust your parameters based upon these gradients. So the sort of the key element here really is that first thing. It's the hypothesis class that these algorithms use. So to motivate this, I want to actually bring us through a few steps here and talk about what's called feature learning. So for the most part, we've talked, not entirely, because we talked about things like decision trees too, but for a lot of what we talked about so far in this course was linear hypothesis classes. In other words, our hypothesis was some linear function of our parameters times maybe some features of our input, right? We allowed there to be a feature mapping there, things like a radial basis function or polynomials, but our function was linear in the parameters themselves. That's the hypothesis class we largely used. And so the interesting thing here is that this depends then kind of crucially on your choice of features, right? As you may have seen from some of the homeworks, you can pick different features for your problem, and this is largely, in a matter of engineering these things, what these features actually are. And this will give you very, very different performance on the task at hand. So if you pick, good features, you can do very, very well on task. Whereas if you pick maybe just the raw inputs as features, maybe that does very poorly. And this has kind of been the state of machine learning for a long time. The secret was it crucially depends, the performance of your algorithm kind of crucially depends on what features you choose as your sort of representation of your input. And so the key question kind of that would emerge then is, well, why do we limit ourselves to just learning the parameters here and hand tuning the features? Couldn't we also learn the features themselves? And this is actually the way that I want to motivate neural networks as a kind of a way of learning features or thinking about learning features. So let's take a few stabs at this. And so in the first stab, we're going to use this linear class of hypotheses and kind of extend it. So what if, so I'm going to write it like the following. I'm going to write our hypothesis as W transpose phi of x plus b. So all I'm doing here is that for convention, I'm separating out my bias term, the constant feature term, from the rest. You don't have to do this actually. You can leave everything as it is with the bias in there, but it kind of is actually a pain with neural networks sometimes. So it's much more common to see that you'll replace the constant term there with an explicit bias term. And in this case, let's actually also go further. And so this is the linear function now of our features. That's the same as we had before. I'm just using different notation here. So W would actually be a 1 by k matrix, and B would be a scalar here to get a scalar hypothesis prediction. But let's go a little further here. Let's also replace this term here. Let's call this 2 and 2. Let's replace this term. Instead of having a fixed set of features, let's just go ahead and make the features a linear function of the input itself. So let's make the features actually be equal to W1 times x plus B2, where I guess I'll give sizes to all these things. So here W2 is going to be in R to the 1 by k. B2 is just going to be in R. W1, assuming our x is n-dimensional, it would be a k by n dimensional matrix, and B1 would be in RK. So that just makes all these things kind of fit, the multiplication fit. And I said, in this case, our parameters theta here is just shorthand for all these things. So I'm going to use theta, but of course theta really means a set of all the parameters we have of our learning algorithm. So there's a problem here. Does anyone see what the problem here is with doing this? Yeah. Yeah, so the answer was that we haven't actually improved our representational power here. And the reason is the following. I'll just add, we could draw this something like this. I'll get back to that actually drawing in a second. But the key problem here is that if I write this out, I have W2, W1, X plus W2, W2, B1 plus B2. And so this is still a linear function of X, right? This is just, I'll call this thing here W tilde, and I'll call this thing here B tilde. And then this is just equal to W tilde X plus B. So by having all these parameters, you haven't actually improved the class of functions you can represent with this. You're still talking just about linear functions. So this is a problem because we tried to, the whole point of learning features was to go beyond just linear functions in our inputs, and we ended up back at linear functions in our inputs. So just composing linear functions like this is not enough to actually have us really learn features of our input that are in any way kind of descriptive. So this brings us, though, and I should say we could draw something like this where we have a multi-layer representation of this, where I'm calling our second layer here Z, the Z layer, denoting it by Z, and then the output is Y. So we take X, transform it once to Z, and then go to Y. But the problem is there's no added benefit here to just going straight from the inputs to the outputs. So this brings us to neural networks. And neural networks are a really simple extension of this. They are just the following. We're going to do the exact same thing. All we're going to do is that after each linear operation, we're going to apply some nonlinear function. So for example, depending on how you count, it's either a 2-layer or 1-layer or 3-layer hidden neural network. I'll call it a 3-layer one. But a 3-layer neural network, that means it has an input layer, an output layer, and one hidden layer in the middle. And I'll talk about why it's called a hidden layer in a second. But this just says something like the hypothesis is equal to some function of a linear function of some nonlinear function of my inputs, this, apply a nonlinear function, multiply by another matrix, add something, and apply another nonlinear function. And you can, of course, keep composing these, which we'll do in a second. But it's exactly the same as before. All that's happened is that we've also added these nonlinear functions here. And it turns out this gives you a huge amount more representational power, adding these nonlinear functions. All of a sudden, we no longer can do the trick where we did before, where we just sort of describe this all as one big linear function. And so these functions actually are fundamentally more powerful than linear functions, and often to an amazingly so. Now, of course, the question that remains is what do we choose for our nonlinear functions there? And actually, you can choose a lot of things. So common choices are things like the hyperbolic tangent and the sigmoid function. These are kind of both similarly looking functions, actually. They kind of are S-shaped. But the sigmoid varies from 0 to 1, whereas the hyperbolic tangent varies from -1 to 1. So depending on how you want to scale your features, you can actually do either or. The most common current nonlinear function is what's called the rectified linear unit. It is just a linear function that you truncate at 0. So anything below 0 becomes 0, and everything else is just a linear function. So it's just the max of x and 0. And that seems so simple, right? It seems like it's not even that nonlinear, but it turns out even with that function, that is sufficient, in fact better oftentimes, at increasing the representational power of these things hugely. So again, we draw them the same way as before, actually. We don't bother drawing in the nonlinear functions because the reality is because no one would ever do multi-layer linear networks, the nonlinear functions there are always implied. And so we always assume that between each layer is some nonlinear function. Yeah? The question was, does the rectified linear unit perform much better than the sigmoid function? The answer is yes. It's unclear why. I mean, there's a lot of theories as to why, but we won't get into that too much. There's things about, the gradient's always better to find in one direction. You always have a gradient, whereas the sigmoid has very little gradient on both ends, but that's sort of a very empirical fact. There's no real fundamental reason to that. I'm just speaking from experience there. Okay, so we're going to draw the neural network like this, where we have our inputs, our what are called hidden units or activations, which I'm going to call Z, and then the output Y. And these are called, and basically what I'm doing here is I'm calling this thing Z. I'm calling it Z2, I guess I'm calling it Z2. And the reason why I'm doing that is that this set of activations or hidden units Z, there is nothing in the data itself that prescribes what value those variables should take on, right? They can take on anything they want as long as they sort of help you in the end give good predictions. But they could take on any value. We never observe what those things should be. And in this case, it actually bears some similarity to the latent variable models we talked about when we talked about probabilistic modeling and anomaly detection. But they're also actually quite different at the same time. There's no probabilistic interpretation here. They're just some numbers that allow this function to be very expressive, with it's the explicit case that these things don't really necessarily have any true meaning. They might by happenstance, but they don't need to. They just need to help you make a better, more expressive predictive function as a whole. So that's the nature of those hidden units there. And there are a couple of sort of nice properties, or nice and then not so nice properties of neural networks. The first is that neural networks with a single hidden layer, so that's this one right here. So we only have, or this one here, we only have one hidden layer, one set of hidden activations. Even in this case, they are actually what are called universal function approximators, meaning that you can take any function of your input data and you can represent that with a neural network with one hidden layer. And that actually holds for a wide set of possible activations. You can do it with sigmoids, you can do it with rectified linear units, you can kind of do what you want. Now, in practice, that's sort of nice, right? It means that we're talking about a very rich class of functions, but that isn't that useful in practice because this requires actually a very, very large number of these. So these have to be really big. It has to be in some RD or this is RK, I think, where K is really big. Right. So it's actually similar, kind of in spirit, to the fact that polynomials are universal function approximators, right? So given a high enough degree polynomial, we can approximate any amount of data. That's great, but isn't really that useful. That's not really what we care about. We're just fitting the points exactly, right? So the same thing is going on when we talk about neural networks being universal function approximators. It's a very odd way you actually go about constructing these things that can represent any function. But what's impressive, I guess, what actually makes these things interesting is the fact that they actually seem to work much better than a lot of other function approximators we know about. So they seem to work much better than polynomials for a similar size of complexity, the number of parameters. They seem to work much better than polynomials, and so we like this better than trying to use something like a polynomial. The other thing I'll mention is that the hypothesis function in neural networks is not convex in its parameters. Again, all that means in our context is that we cannot find the absolute globally optimal set of parameters to minimize some objective. We need to just run gradient descent and hope that we do okay. But again, kind of surprisingly, and for a long time I'd say this is kind of what turned people off about neural networks. I think turned people off to them. So I think that this was seen in light of methods like support vector machines, or actually even boosting has a kind of interpretation as this gradient descent on a convex loss. These things were kind of seen as a big negative for neural networks because we didn't know how to train them. We wouldn't know how to get a good local optima. But also kind of impressively, what's been sort of understood over the past few years is that actually, despite this fact, it seems to work very well in practice. And the local optima we get tend to actually be all pretty good, even if they aren't globally optimal. They're all sort of good, the ones that work well after you run gradient descent. And there even is some theory starting to come out about why this might be the case, why there are a lot of good local optima for these problems here. And the last thing I'll add, though, is that with these very complex models, there comes a lot of additional complexity in terms of hyperparameters. So you can think of the entire, the values of these weights themselves are parameters. So what the value of the weights actually take on are parameters, but the actual number of all of these things, how big, how many dimensions, et cetera, do you want here? That is all a hyperparameter, right? So you can choose how big you want your neural network. You can choose how many layers you want, et cetera. Those are all hyperparameters, and there are a lot to choose from. You can really choose from a lot of potential architectures there. So this brings us to deep learning. And deep learning, while it in theory can actually mean a lot of things, in practice it really just means machine learning using multi-layer neural network architectures. That's sort of what it means in practice. I think that there was, at least initially in deep learning, a little bit of a sense that it could mean any deep architecture. It could mean probabilistic models that had multiple layers, et cetera. But really right now, it just means neural networks with multiple hidden layers. So what you do is you basically do the same thing we did there. You just repeat this process multiple times. So the way I'll write this is that you have this sort of recurrence that defines your layers. The layer, the I plus 1 layer is equal to, or the activations for the I plus 1 layer is equal to some nonlinear function of some matrix times your previous layer plus a bias term. And the final hypothesis, and by convention, the first layer is considered just the inputs, and then the hypothesis function of x would just be equal to really the last layer, zk. Right? So this is sort of how you would compose many of these things together. You just keep applying. This is a little bit cleaner to write than just manually putting this all through each time. So this is sort of the recurrence that defines a deep neural network. One thing to importantly note here is that this zi here refers to a whole vector, not an index into a vector. Same is true for bi and wi2. These things I'm indexing over I. Because I've run out of other indices, but that does not mean the ith element of a vector. It means an actual vector itself, and you have a different one for each layer in the network. Now, the question kind of comes up naturally is why do we use deep networks? Why don't we? We already know that this is a universal function approximator with a single hidden layer, and even if that's not that useful in and of itself, why do we want to actually use deep networks? Why not? If we have a fixed set of parameters, why would we want to use a deep network as opposed to just a single layer network with maybe more parameters, a larger weight matrix W, right? And there are a few kind of motivations for this. None of the sort of higher level motivations are that convincing, I don't think. First of all, there's this notion of motivation from circuit theory, which says that some functions, for instance, the parity function. So parity is if you're given a string of bits, you want to say is there an even or odd number of ones in that string. That function you can compute, in order to compute it with and I won't go into details here, but I'll just sort of say, and you can kind of maybe imagine why this is the case, that if you compute that function with a single hidden layer network, it would take 2 to the n hidden units to represent that. Basically, all you could possibly do for the parity function is just enumerate every string, essentially encode every possible numbers of zeros and ones in your input, and have each one correspond to each string corresponds to a hidden unit, and then if that one's on, you predict that parity. the parity for that one. Alternatively, though, if you have a multi-layer network, you can actually kind of play a contest where you look at the parity of 2 bits first, and look at the parity of the next 2 bits, and then do that recursively, and that will actually also give you the parity. And so you can actually construct a network with only order n hidden units if you use log n depth to your circuit, which is a nice result. But I should also add, it's really not clear if deep learning is doing anything like that. It's not clear that we are learning functions that are fundamentally hard to represent with shallow networks, or whether they just somehow work a little bit better. In fact, for the classes we talked about so far, which are these fully connected dense networks, it actually is often the case that you can take a trained deep network and approximate it with only one hidden layer with the same number of parameters, and it does almost as well. So it's really unclear that one is actually happening, at least in the case of fully connected deep networks. Yes, question.
It always seems to me like these with the deep learning, it's with the difference between the shallow and the deep networks, and then you get recursive deep neural networks and stuff like that. Is there a lot of science, hard like mathematical evidence behind those, or is it more anecdotal and just experimental?
I think I'll repeat the question mostly, so I think I'll get to most of those points here. It's largely, I mean, the advantage of deep networks is largely experimental. In fact, I'm going to get to the last one. That sort of is the last point, maybe.
How do you decide to do like, oh, let's take a neural network and add more layers to it, oh, let's take a deep network and then like add pointers for the...
I'll get a little bit to how you go about making these architectures in a little bit. I don't think that's something I really want to cover too much in this class because it's not really data science. And so I actually want to get away from architecting architectures for deep networks. Okay, so the second motivation that people often mention is from biology, right? So the brain has multiple layers of interconnected neurons. We call these things neurons and neural networks as well, so therefore they must be the same thing, or at least using similar processes. And of course, the response to this is that despite the name, there's a incredibly weak connection between neural networks. It's a wonderful name. Again, we're really good at advertising in machine learning. We're doing a great job. Support vector machines sounds very cool. Neural networks sounds very cool. But there's virtually no connection between what's happening in the brain, which we really are only barely understanding at a very, very small grain level, and what happens in neural networks. And I think that thinking of them as anything being in any way biologically inspired is really a incorrect statement. And they should instead be thought of really just as function approximators. They are a rich class of functions you can use. They are in no way related to the brain, especially when you have hidden units like rectified linear units, which have no analog in the brain. So don't think of them as bio-inspired, despite the name. It's a cool name, but that's what it is. And so the last point really is that the ultimate motivation for these things, honestly, is they just work better. They seem to work better when you have more layers, especially for things like images and things like this. They seem to just work much, much better than anything we had before. So that's hard to argue with. The other two I would definitely argue against, that really being the motivation for deep networks. But the third one is very hard to argue with, even though we don't really know why. Okay, so let me now switch to talking about, and I have maybe I'll get through everything here, maybe not. I have to do a little bit, I guess, next Wednesday, but hopefully we'll get through it all. I'm going to talk a little bit about training neural networks. So again, when we think of these in the context of our machine learning framework, we talk about a hypothesis function, which is that really is the neural network itself, the hypothesis class. We talk about a loss function, which is really just the traditional loss functions. So for example, if I have a binary classification task, I can use logistic loss to measure how good I am at predicting a binary -1, +1 label, right? And we went through this with you can use hinge loss too for a support vector machine. You did all these things, so those should all be familiar. So now the question is, given the loss function, the hypothesis class, how do I optimize this, the canonical machine learning problem? I could also add some regularization on theta if I wanted. It doesn't really, I'm going to leave it out for now just for simplicity. And the answer there is actually also very simple. It's just, well, use gradient descent. We can't, unlike least squares, say, we definitely don't have any analytical solution to the best set of parameters. In fact, we can't even find the best set of parameters because the problem has local optima, so we don't even know that we found the optimal set of parameters. But instead, let's just use gradient descent as kind of a local heuristic, though that sounds kind of worse than it actually is, to find a good setting of our parameters, even if not the best ones. But in fact, we're actually not going to quite use gradient descent as we've been talking about it so far. We're going to use actually a method called stochastic gradient descent. We'll talk about this a little bit more when we talk about big data and kind of machine learning for big data, because it's very prevalent there. But the basic idea here is that when you do start having these relatively big models and relatively large amounts of data, then gradient descent, as we described it so far, becomes very, very slow and inefficient. And the reason is actually pretty straightforward. So in gradient descent, what you do is you take your objective here, right? This is your entire objective. That's the sum of losses on all your data points. And I compute the gradient of that sum of all the losses, which is just by linearity the sum of the gradient. So I compute the gradient on all my examples, given my current set of parameters. And then I update my parameters by taking a small step in that direction. And then we repeat that process, and that gives us eventually a good set of parameters. The alternative approach to this, which is actually quite a bit better, performs much better in practice, is something called stochastic gradient descent. And the idea of this thing is that instead of kind of computing the sum over all, instead of computing my actual gradient over the entire sum of losses, I'm going to compute my gradient with respect to just one example, where of course I'm going to then iterate over all my examples. I'm going to choose different examples, but I'm going to compute my gradient with respect to one example at a time. And I'm going to adjust my parameters based upon the gradient on just that one example. And you can think of that like this is a very, very noisy approximation of that thing, right? Because it only takes one example into account. If it's a positive example, it'll push you one way. If it's negative, it'll push you the other way. But if I loop over all my features then, in some sense, on average maybe, I will still get a good set of parameters because, they'll keep pushing me in little directions here and there. I have this step size alpha to kind of make sure I don't take too big a step in any given direction. But that's kind of my idea. So I'm gonna take small steps in the direction of individual examples. And actually, I want to highlight this in another way about sort of what these algorithms really mean programmatically. And this is sort of gets at the heart of why you might want to use stochastic gradient descent. And so for gradient descent, what we do is we repeat the following process, right? We first compute these little g terms, and that just means we're actually computing what those gradients are with respect to every example. So we have to compute them and then store them, or at least store their sum. And then once it's computed all of those, then we update our parameters. So if that gradient computation time takes a lot of time, we have to wait a long time before we update our parameters, right? We're waiting a long time before we give our first update. In contrast, with stochastic gradient descent, every new example, we're providing some update of our parameters, right? So every time we see a new example, we're much more quickly adjusting our parameters. Now, of course, there are trade-offs here. The exact gradient descent is actually going to have much better guarantees of convergence to an exact solution, whereas this one oftentimes will not have. Oh, I forgot the alpha here. There's supposed to be an alpha there. But it will oftentimes not have great proofs or great sort of convergence guarantees, though you can actually do some fancy theory and actually get better guarantees. But especially when this gradient takes a long time to compute, or if you have a lot of data points, so it would take a very long time to sum over all your data, this procedure here seems to work much, much better because you can kind of make some progress before looking at all your data. And if you can think of your data as belonging to some, there's hopefully some pattern in your data, right? There's some regularity there. You tend to exploit that much faster with this method here. Yeah?
Because there's a larger chance of avoiding local minima over here?
So I'm not really going to get, so the question was, is there a larger chance of avoiding local minima here? There is an element to which this adds a little bit of noise to the process, so you may avoid, you may like kind of be able to jump out of some local optima, you know, if one example pushes you one way, the other one pushes the other way. I'm going to actually not talk about that too much as a motivation here. It's more just a matter of speed in my mind rather than local optima avoidance, though that is a factor. I do want to mention that, but I didn't mention that, but you mentioned that. Yeah.
So just to clarify, you're still using all the samples in this?
Yeah, so I'm just talking about training right now. So I'm assuming that you have, you know, some training set which has I1 to M. This is not about evaluation at all. This is just given a training set. And I'm still going to iterate over all my examples I equals 1 to M. So I'm still going to use every example to update my parameters. It's just that in this case, I'm going to sort of do that one example at a time and update every time I compute a gradient for one example. Whereas in normal gradient descent, I would actually be computing, and this is what you did, in fact, I would be computing all my gradients over all my data points and then updating based upon the sum of all those things. Okay, so now this leads us to the, I've sort of pushed this off as long as I can at this point, but how do we compute those gradients, right? And of course here, theta is not really a vector. Theta, again, was a set of parameters, right? So what we really are asking, you know, what that really means is, how do we compute gradients of this hypothesis function, wherever that one there is, with respect to all the different matrices or vectors in theta, right? And here I'm going to not tell you how you do it exactly. This is a technique called the backpropagation algorithm. And I was sort of sad when I decided not to leave this out, because I really love teaching this algorithm. It's a really simple algorithm that actually is it's beautiful and very, very simple. If you want to learn it from me, you can take 15780, which is the graduate AI course next semester. If you want to learn it from other people, they teach it in almost any machine learning class these days. So I think 701 or a 10701, things like that. You will learn it there. I'm not going to teach it, but really all it is all backpropagation is just an application of the multivariate chain rule of calculus to compute those gradients there. So that function there is a composition of multiple functions, right? Because in a neural network, we sort of compose multiple functions inside of each other. The way you compute derivatives with functions like that is that you use the chain rule. You just take gradients and pop things out and evaluate gradients at certain points, etc. And all backpropagation is just the chain rule. That's all it is, applied to neural networks. The other thing it does, though, is what you'll find is if you use the chain rule to compute gradients with respect to this and this and this and this, you'll find that you actually repeat terms multiple times. So a lot of the gradients will involve the same computation, the same kind of multiplication of matrices here. And so backpropagation actually kind of caches these things, caches some intermediate products to speed up the computation of those chain rules. But that's all it is. Right? So it's just an application of the chain rule of multivariate calculus. And it's still a very nice algorithm, though, so if you want to come learn it, I teach it next semester. Now, the other good news, though, is that you probably, even I, don't ever implement that myself. I mean, I do for a problem set to make everyone do it, but then I don't after that, right? Because there are, right now, a huge suite of tools you can use to actually compute gradients for you. So libraries like TensorFlow or Torch or Caffe, MXNet, many, many others, these all on one level, actually, what they are providing you is they are providing you a way to specify just kind of what I call the feed-forward computation. You specify kind of like what the architecture looks like, what the functions are going forward, how do you compute the function, and then these libraries will compute the gradients for you. And they do it in a very general way, which lets you specify a lot of different kinds of functions, where you can basically build your network and then get a gradient kind of for free. You don't have to worry about how the backpropagation works. So that's actually what, at its core, a library like TensorFlow is doing. Actually, TensorFlow is doing a lot of things. It's also building computation graphs and things like this too. But one of the things TensorFlow is doing is it is building an automated way to compute gradients for computations you specify. And if all goes well, I'm hoping we can use one of these on the homework assignment so you actually can play with it a little bit. There is a non-zero chance that we will not be able to get it on AutoLab, so that may have to go by the wayside, or may at least have to find a different way of evaluating this than submitting code with TensorFlow or one of the others, but we'll see what we can do. Because it's very good to know how to have some experience with these libraries, and it's very useful. So as a data scientist even. Okay, so let me, yeah, question.
Implementations like TensorFlow.
If we have them on the homework, which I hope we will cover the libraries in the recitation section. So we will cover how you use them in that section.
Not how you use them, but like what makes TensorFlow, okay, it's a deep neural network, but what's the difference between TensorFlow and Caffe?
I won't cover that, what the difference between TensorFlow and Caffe is. We'll just give you a library and you can use it. If you're curious, there's lots of stuff online about that. Right? I'm happy to answer that, but we won't cover it in class. Okay, so let me say one more thing before we jump into data science and deep learning. And that is that for the most part, all the success you've seen from neural networks, so all the stories, all the articles you hear about them, they are never using a neural network like I just described. They never actually use a function like that, where you have a matrix that you multiply, a full matrix, you multiply it each time, and apply a nonlinear function. What they are instead doing is they are actually using much more specialized operators in the neural network. Specifically, the two most common are convolutional neural networks and then recurrent neural networks. And actually, even in recurrent neural networks, there's a further specialization, which I'll talk about in a second. But the ideas here are actually quite simple. So I'm going to talk about convolutional neural networks first. And I'm going to motivate this by saying that fully connected networks, these are networks where you have your entire input, and you multiply it by a great big matrix, and that gives you another set of hidden units, and then you do that again. And, you apply a nonlinear function, and you do it again, et cetera. If I were to say apply that to an image, this would be a really hard thing to do, right? So a 256 by 256 image, this RGB, is about 200,000 dimensional inputs. So if you encode each pixel as 3 values, right, for the RGB, you get about 200,000 dimensional input. And if we were to apply a fully connected network to that size image, we would almost be guaranteed to overfit to our data set, right? Because there's a ton of parameters there. If we have, for each image, we can multiply by 200,000 different numbers. We do that multiple times. We're talking about a lot of parameters here. So it's probably going to overfit to our data. And secondly, it isn't really a very good representation of what we think about as images, right? Because images have certain what are called invariances. And that means that if I take an image of a dog and I shift the dog over 1 pixel, it's not a different image. It's actually the same dog. It should still be classified as a dog, even though the dog shifted over 1 image. But if you have a network here where each pixel has its own weight, there's no guarantee that the weights for these pixels are going to be the same as the weights for the pixels when you move the dog a couple spots over to the left, right? In fact, it probably won't be the same weights. So we're missing some of the natural characteristics that images actually have. And this leads us to an architecture called convolutional neural networks. And that should say these are probably actually what has made deep learning successful, or convolutional neural networks. There's other classes too, but these are by far the workhorse right now of deep learning. And so the idea, all we're going to do is we're going to apply what are called convolutions to our input images and have our subsequent layers be actually convolutions of previous layers instead of just arbitrary linear operators. What this means is, just sort of in quick terms, is that if I have an image like this, I take an entire region, an entire rectangular region, and I apply some set of weights to that. And by apply, I mean this set of weights is the same size of that region, and I multiply the weights corresponding to each pixel, add them all up, and that becomes a single activation in my next layer. Okay? Then I slide my weights, or my little window, over by 1 pixel, do the exact same thing, importantly with the same weights, and that becomes the value for my next activation. And it's kind of actually hopefully somewhat apparent that if you do this, there's a certain kind of invariance you get, because you're going to get the same sort of set of weights applied to the pixels, whether or not your dog is shifted over to the left 1 pixel or not, right? You get the same kind of inputs. And I'll talk about in a second actually what these look like in practice. It's also common to reduce the size. I mean, this one actually will reduce the size by a little bit if you use the right thing. Maybe you get rid of the edge pixels, but that doesn't reduce the size that much. So you can also reduce the size further by applying what are called max pooling layers. This just take the certain, all the pixels in a certain area and set the activations in the next layer to be the max of all those activations in the previous layer. So that's the max pooling layer. So you have convolution layers, max pooling layers. You'll also have nonlinear functions, but these are all kind of the same. Basically, these things just replace this operator here with a specialized operator like the convolution. And I should add, these are also, maybe I said this, yeah, I actually say it here again. So in practice, actually, you use what are called 3D convolutions. They're not quite 3D convolutions in the normal sense. They're all really like multi-channel convolutions. The idea is most images have multiple channels. So you have a red, green, and blue channel. And so your weights actually here correspond to weights for all 3 channels, kind of like one slice of weights for each channel. You add all those up. You take all your weights, multiply them by all the corresponding channels and positions here. You add this all together, and that becomes your activation in the next layer on one of the channels in the next layer. And you have another set of weights that specifies what the next channel's activations are. And so actually, you can construct multiple channels at each different layer using multiple different versions of, or multiple different convolutions that all sort of use all the previous layers, all the previous channels. So this is a little bit more complex. It turns out you can represent all these things as tensors. So that's why it's called TensorFlow, is that these things are like 4-dimensional arrays used to represent everything. But really, it's actually just a matter of sort of bookkeeping in a certain sense. Yeah. Okay, yeah. So that's a great question. So the question was, isn't this cross-correlation, not convolution? And you're absolutely right. So convolution is the same thing where you flip you invert the order of the filters, actually, or you flip the filters upside down, and you also do something different at the edges. So you're absolutely right. So actually, when people in neural networks say convolutions, they actually mean correlations. It's just that we use the term convolution to mean that one. So sorry, that's completely standard to use correlation filters, not convolutional filters, but you have to get used to that. That's what they mean by convolutions, are actually correlations. So if that doesn't matter, if those terms aren't familiar, don't worry. But from the signal processing standpoint, what we're actually doing here are correlation filters, not convolutions in the true sense. Convolutions would actually be, you would flip upside down and left-right the filters before you apply them, and you do something different at the edges. But don't worry about that. That's just sort of, I don't know why. They're just simpler. The convolutions kind of sound simpler, too, than correlations. Or it sounds like it's more descriptive somehow. So that's why we use it that way. Great question, though. OK, so that's, I thought I had a, hang on. Oh, I guess I'll just go back. So after this point, you should now be able to understand what I mean, what this architecture AlexNet actually means. So AlexNet here means you have your initial image is 224 to 224 with 3 channels, the RGB channels. I apply a bunch of 11 by 11 filters, and I apply 48 of them to get another layer, which is, that thing convolved with 48 different filters to get this big thing. I apply more convolutions to get then 128 channels, more to get 129 channels. The convolution filter sizes are first 11 by 11, then 5 by 5, then 3 by 3, then 3 by 3 again. I I have some max pooling in there sometimes as well. That just takes a layer and it makes it smaller. And then at the very end, kind of crucially also, I then take all my activations and I stack them in a big vector, and I then apply some dense layers to that. So I have a few of these kind of layers at the very end of my classifier there. And that's how I get my classification. In the last layer, I have 1,000 different dimensions, and that corresponds to essentially the indicators of which class out of those 1,000 is most likely. So that's what this figure actually means. It's cut off because they actually represented it on 2 GPUs, and so it was the same architecture just spaced across 2 different GPUs, and that's how they trained it. That's actually the figure from the paper. It is actually cut off in the paper. It's not that I did not clip it. It's one of the most famous truncated pictures in maybe they did it for space or something like that in the submission, but one of the more famous truncated architecture pictures in machine learning. So those are convolutional neural networks. The other kind I'll mention kind of even more briefly is recurrent neural networks. So the idea here is actually one of predicting sequence data. So oftentimes we don't really have a bunch of independent examples we want to predict. We actually have a whole sequence of outputs we want to predict given a whole sequence of inputs. So things like time series forecasting or sentence labeling or part of speech tagging. These are all cases where you have a whole series of inputs and you want to assign an output to each of them. But you don't want to do this by treating each input independently, because then you miss a lot of important characteristics about it. So this leads us to what's called a recurrent neural network. And the idea here is actually very similar to other neural networks. You have some hidden layers here. So for Z1, 2, that's like X2, I have a hidden layer for that, and then I predict my final layer there. But importantly, my hidden layers are also functions of the previous hidden layer sequentially. So I basically make my hidden layer, and I can stack these also and make them deep. This is just showing a shallow version. My hidden layer is a function both of my input and my previous hidden layer, and then I predict my output based upon that. And what this lets us do is this lets us actually retain some notion of the state of the system within this hidden set of activations there. Within those activations, you can actually maintain kind of what the current state of the system is for some definition of what state means. And the reason why is you can kind of persist that, right? Because if I had some characteristic of this example here, I can encode that in my hidden activations here, my hidden layer here, and maintain some of that information in my next one because I'm sort of always propagating this forward. So think of it kind of as in terms of the flow of information, right? That prediction there, Z2, so superscript 2, can depend not only on Z1, 2, the input, but also on all previous ones in theory. Now, again, kind of in practice, it doesn't quite work that way. That architecture will have a hard time capturing long-term dependencies, and so people actually use something a little different, well, a lot different, a lot more complex rather, called a LSTM, which stands for a long short-term memory cell or long short-term memory network. And the idea here is that instead of sort of a simple one simple nonlinear function to give hidden states from other states, you actually have a much more complex set of hidden layers and other things, and they're called gating arrays and things like this. So you have your input here, you have some hidden layers, you have your I forget what C stands for there, but it stands for something, and then you have a bunch of other operators here like forget and input and output, and these things don't really matter. But the point is that this is just all this is just a more complex form of this function here, which tends to preserve long-term dependence better. And so almost all recurrent neural networks actually use some form of LSTM or some recent similar innovation. Okay, questions? We can all go implement these things now, right? It'd be no problem. Okay, I think actually I might get through this in the rest of class. So let me talk about now, come to the crux of this talk, which is really about deep learning and data science. Because when it comes down to it, deep learning is really kind of advanced machine learning. And it's really unclear, at least, whether this has any role in a data science course, right? Because we're, for the most part, satisfied with pretty rudimentary analysis. I mean, even though the polls were wrong yesterday, I don't think they would have been better had they used a deep network to predict better, right? To somehow fix them. That was a more fundamental problem. And remember, in the first lecture of class, I sort of threw up this figure here. I was sort of saying on this page. So I'm going to talk about now deep learning and data science. So in the first lecture of class, I threw up this figure here, which was talking about sort of the universe of all solvable problems, or sort of all problems you would like to solve. This is completely inaccurate, the proportions here. Probably much fewer are actually solvable. But of some data problems. So of the problems that you guys proposed or wanted to propose for your project assignments, probably about half of them are impossible. So we got a lot of proposals about stock market analysis, and I'm just going to tell you right now that's impossible. You're not going to be able to beat the stock market. Maybe you can if you can do stuff if you can trade at really high frequencies, things like this, but in the span of a course project, you're probably not going to succeed at finding some strategy which is going to make you money in the stock market. So that goes into the unsolvable problems here. We can still do it, by the way, but still unsolvable. The other half maybe are solvable. So maybe you have a problem which you actually can apply a machine learning algorithm to and solve. In my experience, the vast majority, and again, these are made up numbers here, but the vast majority of these can be solved with relatively simple algorithms. So I mean things like linear regression or linear classification, and maybe nonlinear regression with something like the RBF bases, right? Maybe that, if you want to get fancy. And maybe if you want to be really fancy, something like boosting might also help you, right? Very, very few need deep learning. Right? Very, very few problems actually require these things will not require these things to do substantially better than you can do with existing techniques. Now, I should qualify this a little bit and say that I think this is mainly true. What I really I'm talking about here is new deep learning. So very few problems are of the category where you need to develop a new architecture, kind of train the architecture as a deep learning system, or even use as existing architecture, but a standard kind of architecture, train it from scratch on your data, and then see how it actually does on your problem. So. The short answer for how you use deep learning in data science is don't do it. Don't try to do it. If you have a problem where you have kind of traditional features, and what I mean by that is like features like we had with our classification example. They were things like, this is for the tumor example, things like the size of the tumor or concavity, kind of things that are human interpretable. If you have those features to describe your data, do not just throw deep multi-layer perceptron at your data and think it'll work. Instead, first try linear regression. That may work or linear classification, depending on your task. That very well may work in and of itself. Then try, maybe something like nonlinear RBF features. I'm a fan of those as a quick next check. Try something maybe like gradient boosting too. Those certainly are all work, and they're all much less finicky than deep learning algorithms. So if you try to solve it with a deep learning algorithm first, chances are you won't know whether your performance you're getting is due to the inherent hardness of the problem, or due to the fact that you somehow picked the wrong architecture and it's just not quite good enough, not expressive enough, or there's some other problem that's preventing you from training it well. They are much more susceptible when you don't know a good architecture to sort of getting stuck in, hyperparameter search doesn't really improve things, and chances are you'll do much better, much faster if you apply the other methods first. Now, the exception I'll say here, well, I'll mention some much more important exceptions later, but the exception I'll mention now is if the techniques that I mentioned in the second line here do not solve your problem. If they, if you run those things and they don't work, well, chances are actually you're then in this domain here. You're in the unsolvable problems, and we'll talk a little bit about a little bit more later about how you maybe recognize when you're there versus not. I think actually we'll have a lecture kind of on those issues in particular. So you're probably here if nothing is working for you. But there is some chance you're in this little range here, right? And a good way of knowing that actually is to see if you can visualize your data in a way that lets you solve the problem. Okay, and so this is actually a really important thing here. So vision is a domain like this, right? Because we tried to apply a lot of machine learning to image classification. We couldn't do it, yet we can do it, right? Humans could classify images pretty well. So somehow we are solving the problem, and our machine learning algorithms were not able to. This is a great domain for deep learning. It's where we know there actually is an achievable performance that we can solve, we can get to, but yet our current algorithms are failing at getting us there. So if that's the case, then yes, you can go ahead and apply deep learning. You're probably then in the domain of much more traditional machine learning research than real data science, but by all means, you can go ahead and apply deep learning there. You can also apply it if you've really kind of maxed out your performance. If you've tried, very detailed, a lot of different types of features, lots of manual features. With those features, you try a lot of different algorithms like boosting, like nonlinear regression, et cetera. You've tried all those things, and you get good performance, but you really want to squeak out. Maybe your revenue is exactly dependent on the performance here. So a 2% boost in performance is equal to some however many millions of dollars in increased revenue. Then by all means, go ahead, try to apply deep learning using your current system as a benchmark, so you sort of know what you're aiming for there. But those are sort of the two exceptions for general problems about when you might want to attack something with deep learning. The other big exception, though, is with structured data of certain types. So it is undeniable that deep learning has been hugely successful when it comes to structured data like images, and I actually can almost enumerate them, right? Basically, it's images, it's audio, and it's text. At those things, which are very hard to do any sort of detailed machine learning on, they've been kind of foundational challenges for a long time, and they do come up in data science problems, right? There's plenty of times where we do want to classify an image, right? So when that happens, by all means, use deep learning. But don't train your own deep learning algorithm on it. That's oftentimes very hard. Again, you're going to run into all the problems of large number of parameters. They're slow to train. You need to sort of figure out what's going on here. You can do that, but if you want to do that, then you're really doing machine learning research. So learn how to do machine learning research then. If you just want to do data science, don't do that. You'll waste a lot of time. What you should do instead is use an already trained network, an already trained model, as a way of generating features for your task. And this is actually what we'll do on the homework if we get TensorFlow or something else to work on AutoLab. I will not make you write a new neural network, at least for 388, maybe in 688 you can, if you're feeling masochistic. But we're actually going to be doing this. So here's an example. I mean, not a worked example, but just a sort of an example of what this kind of stuff means. So a subsequent, after AlexNet, a subsequent very popular neural network architecture for image classification is called VGG. I forget what it stands for now. It's from some Oxford Vision Group's acronym, I think. But the VGG network is basically a really big convolutional network with lots of convolutions and max pooling in there. And you actually can look. There's 19 layers of weights. You have convolutions. They're all 3x3 convolutions here. They're all small convolutions. That was actually the kind of the innovation of this network. They're all small. Then you have a final max pooling layer. You have a fully connected layer of 4,096 units. Another one of 4,096, and you have your last one, which is 1,000, and that last one is the actual classes you're predicting on ImageNet. So this network was trained to classify ImageNet images, right? So it's trained to classify those ones you saw, the Dalmatians and the cherries and all, Madagascar cat and all those kind of things. So this last layer here, basically is our last layer, which is going to tell us which class our image is. And so if you look at a neural network, though, if you look at every layer but the last one, right? The last layer actually is kind of just a linear classifier, right? In fact, it is just a linear classifier in most cases. So the second to last layer kind of are the features that last layer is using, right? So our second to the last layer of our network, those are features. And they are features certainly that are trained for that task. But what's amazing about these things is they tend to actually generalize pretty well to other tasks too. So take this network, chop off the last layers, and use the second to last layer, or maybe the third to last layer, or something toward the end. Use that as your features that you input into the algorithm that you have. Those will typically work much better than kind of other standard off-the-shelf computer vision algorithms that you may use and computer vision features you may use. And it's actually been kind of amazing at just how good some of these kind of features really are. So do that. Don't try to train your own network from scratch on your problem set. It probably won't work very well. Take an existing network, use the last layer of weights, and use those as your features. You can also, if you really want to, you can also do a thing called fine tuning, which is essentially the same thing, but you start with the network and you fine tune a couple more layers. So maybe you actually, adjust this last layer of convolutions a little bit to make things a little bit better. And finally, I know I'm out of time, but the same thing you can do for text. So if you have a text classification task, don't use Bag of Words or TF-IDF. Actually, download this library called Word2Vec. It's a pre-trained deep neural, or actually not even deep, I think. I think it's actually fairly shallow, but it's a pre-trained neural network classifier that basically is built to try to classify context of words based upon the words themselves. And there's a whole bunch of pre-trained libraries that will give you, essentially, for any word from any number of documents, it will give you an embedding of that word in a vector space that captures much more accurately if you use those words in a vector space as your features instead of, say, Bag of Words. You will often do much better at capturing the content in a document than you will with just Bag of Words. So because it actually captures similarity of words, it captures differences of words, these kind of things. So use pre-existing. These are very, very useful. We want to exploit the power of deep learning. Don't try to train them yourselves from scratch. Use pre-existing libraries or pre-trained models, really, as features for your larger data science pipeline. So that's deep learning and data science, and all we're going to say about it in this class. So we probably will have some homework about it too. So we'll probably cover it in recitation as well. All right. See everyone soon. Again, not here next. I am not here next Monday, but I will follow up with more details about that on Piazza.